welcome everybody to day 2 of the workshop on federated learning and analytics. We're so excited to have you all with us today. We have a very ambitious agenda for today. Next slide, please. So we're going to have 2 academic keynotes, one by Adam Smith in a bit, and one by Musharraf Chowdhury at 11:20. We're also going to have a set of lightning talks after Adam's talk, separated into 2 tracks, and we are going to have a set of Google Keynote talks spanning federated learning to analytics to systems and scale. And the biggest event that I'm personally excited about is the poster session, because we have more than 37 posters from students, faculty, postdocs, and Googlers. And we're going to use that session to socialize, to talk, to summarize the breakout discussion sessions as well. So please use that to learn about the latest and greatest and talk to everybody attending this workshop. Tomorrow, it's optional. We're going to be live streaming on YouTube a day to do research tutorials using TensorFlow federated, spanning all the way from privacy, personalization, federated learning, and analytics. So please attend, please RSVP, share the link with your colleagues, friends, and students. It's open to everyone around the world. Next slide. All right, so this is the lightning tracks for today. We have 2. The first one is going to be on this call, so stay on this call if you want to attend the privacy and security track. Switch to the other one if you want to go to the federated optimization, analytics, and systems track. And we're going to share the Google Meet link in the chat box. Again, if you have questions, please feel free to post your questions in the chat box, and please keep your mics muted unless you are speaking. Next slide. Marco.
Yeah, hello, everyone. For our keynote this morning, we are delighted to have with us Adam Smith. Adam is a professor of computer science at Boston University with research interests in data privacy and cryptography. He's perhaps best known for his groundbreaking work on differential privacy that so many of us rely on. His work in this area has been recognized by a long and fantastic list of awards, including a Presidential Early Career Award, a Theory of Cryptography Test of Time Award, and a Gödel Prize. He'll be speaking today about differentially private covariance-adaptive mean estimation. It's a true pleasure to have you with us. Adam, the floor is yours.
Thank you. Can everybody hear me and see my slides? Yeah, all right, yes, great. All right, so I'll be talking about covariance-adaptive differentially private Gaussian mean estimation. This is based on a talk on a paper that'll appear at NeurIPS in a few weeks that is also available on arXiv, and it's with Gavin Brown and Marco Gabaardi from Boston University, and Jonathan Ullman and Lydia Zakintinu at Northeastern. And just a quick note that Gavin and Lydia are fantastic PhD students who are probably very happy to consider opportunities to work with lots of people. Okay, so broadly, this talk is on differentially private statistical estimation. Differential privacy, as I think this audience basically knows, is a rigorous and at this point well-studied approach to limiting leakage from the outputs of systems that are based on compute their outputs from sensitive data, and it's emerged as effectively a standard for privacy protection in these types of systems. And even though it's been studied now for about 15 years, there's still lots to do in understanding what sorts of learning and statistical tasks we can do subject to differential privacy, and how well we can do them and how we can do them, both at the very practical level and at the level of understanding fundamental limits. So this talk is really going to look at the second bullet of trying to understand fundamental limits, and specifically I'm going to be talking about Gaussian mean estimation, and I'm going to be doing this at this term covariance-adaptive, which I'll explain. It means within a certain Mahalanobis metric. But the way I'd like you to think about it is sort of estimating a Gaussian mean on its own terms in the error metric that makes sense for the distribution. So suppose we're given the following problem. We're given a set of samples drawn i.i.d. from some Gaussian distribution with unknown mean and covariance, mu and sigma. And one way to think about this is that we've got this, cluster of points in space that are our inputs. And roughly speaking, they all live in some ellipsoid that is centered at the mean mu and whose shape is described by this covariance matrix sigma. Okay, so the large directions, that is high energy directions of sigma, the ones with large singular values, those correspond to the kind of long parts of the directions of the ellipsoid, and the lower variance directions correspond to narrower directions of the ellipsoid. All right, so what we want to do is find we want to find an estimate of the mean, which is close to the mean, but in the kind of universe as scaled by this covariance matrix that actually generated the data. Okay, so there's a name for this. There's, in general, there's a family of metrics called Mahalanobis distances that are based on rescaling the standard Euclidean distance, and that this is an example of that. And specifically, we're rescaling in a way that would make, we're considering the rescaling that would make the covariance matrix. Issue, we don't know the covariance matrix when we go into the estimation task. So we're transforming the data to fit the covariance. And just to give you some intuition for what this means, if the covariance matrix were exactly the identity matrix, then this would just be the standard Euclidean distance. If the covariance matrix were a multiple of the of this identity matrix, then when the multiple is large, we're allowing much larger errors. We're not penalizing errors as much. When the covariance matrix is small, we're setting ourselves a much more rigorous standard. So I see a lot of comments on the slide, comments about people not seeing slides. So I'll pause for just a second and just check in to make sure that we're okay.
Yeah, if you want to see the slides and Adam at the same time, please pin the screen that says Washington at the bottom. And if you are not seeing it clear, open the chat box, everything readjusts. So you should do these two things and hopefully you'll get a clear view.
So people are asking how to find Washington. I think you scroll through the participants list to find it is probably the easiest way to do that.
Correct.
But
yeah.
If there are more technical issues, by all means, I'm happy to pause and fix them.
Thank you.
Okay, so I think we're good. We're all right. So in general, what's going to happen with this type of scaling is that we're allowing lots of error in directions in which the data have a lot of variance, and not allowing much error in directions where the data have very little variance. And in this sense, we're tailoring the accuracy metric to the shape of the data. And this is a very actually simple example of something that comes up a lot in estimation, and that is particularly challenging with privacy, is to kind of find methods that automatically provide outputs that kind of make sense given the data, that look like real data. In this case, it's a very stylized model of real data, of course, but an important and a very basic one. Okay, so this is our loss. If I didn't care about privacy, adapting to this loss metric would be really easy. I would just use the empirical mean of the data. And what we get is that if the number of samples I have exceeds the dimension, basically, if it's d over some factor alpha squared, then the Mahalanobis, this specific metric, will be controlled by this quantity alpha. Okay, and so non-privately, this happens very naturally and automatically, and it's like a non-issue. But we'll call methods that pull this off, we'll call them covariance-adaptive, or in the current title of the paper on arXiv, it's called covariance-aware, because they kind of adapt to this covariance. All right, so our contribution is that we give differentially private algorithms that do this. They don't require any prior information about the Gaussian. And they require the number of samples they need is really quite close to what would be needed differentially privately. And I'll state this in more detail in a couple of minutes. But roughly speaking, prior work either requires assumptions on the covariance or ends up with a higher sample complexity because you have to spend samples estimating the covariance matrix privately, and you end up with asymptotically a much larger sample complexity. So what we're aiming for is kind of this sort of best of both worlds, and that is to some extent what we get, with some caveats that I'll explain in very shortly. Okay, so differential privacy, I think probably for this crowd I don't have to spend a lot of time on it, but just to be self-contained, we'll say that an algorithm is epsilon delta, differentially private, if for every two data sets that differ in one record, so in one of these high-dimensional vectors, the probability distribution on outputs will be approximately the same under these two inputs. And approximately the same really means that for every possible event, the probability of that event can go up or down by a multiplicative factor of e to the epsilon, or an additive term of delta. So it's like just a typical, very standard differentially private algorithm is you compute some function of the data that you want to, some function that you want to release, and you add Gaussian noise to that function, and that's what allows you to assumptions on that you're working. So in this talk, when I talk about privacy, keys should hold for worst case data. So the guarantee should hold no matter what hold for all possible pairs of neighboring data sets. The accuracy, on the other hand, I'm only going to analyze that under this sort of Gaussian assumption. Okay, so as a warm-up, let's imagine what would happen if we already knew the covariance matrix of the data. So in that case, what we could do is basically we can always assume that if you know the covariance, you may as well assume that the covariance matrix is the identity, because you can just rescale everything, and that won't affect the privacy guarantees. And so at that point, what you can do is the following simple algorithm. You compute the empirical mean. You add noise to that, and that noise is spherical, just Gaussian noise that's the same in all dimensions. So it's aligned with the identity matrix. And then you just output that noisy value, and that gives you the following guarantee. So you get this non-private sample complexity. The sample complexity you get is a sum of two terms. There's the non-private sample complexity, and then there's some additional cost for the private mechanism. This is just a very standard sort of analysis that you can find turns up in lots of settings. Okay, so that's if you know kind of the scaling with which you should work. But what if you don't? So if you don't know that scaling, then suppose the data is from normal mu sigma, but what you know is just some bounds on sigma. So you know some bounds, some matrix A, such that the data is sort of the covariance matrix is sandwiched between A and kappa times A. In general, that A might as well be the identity matrix, again, by rescaling. Okay, so if you know this kind of rough approximation to the covariance matrix, then again, you can do okay. How well you do sort of depends on kappa. The closer kappa is to 1, the more information you have, and so the better you can do. And again, the idea is you once again add spherical Gaussian noise, but now the cost you pay is the cost you pay in sample complexity will go up with this kappa that controls. Essentially, it's like effectively how well you can condition the covariance matrix of the data based on prior information. So another approach is to actually first approximate the covariance matrix and then use that approximation as prior information. And that gives you some a different additional cost, because now in addition to whatever you had before, you've got this new term that is the cost of getting a rough estimate of the covariance matrix. Doesn't have to be very good, but even just getting a crude estimate of the covariance matrix costs a fair amount in terms of sample complexity. Roughly speaking, it's about d to the 3/2, and that result is due to Kamat, Lee, Single, and Ullman. And So this is like a great sort of general approach, but we wind up with much higher sample complexity. And in some sense, the question we started with was, to what extent is this extra term necessary? Okay, so just recapping what we know. So here are the results I just flew through very quickly. So there's if you know the covariance matrix, you get this term. If you get some rough prior information, you get some additional term, and if you don't have that prior information, then you pay an extra factor that scales with the dimension. So what we were able to do is give a mechanism that sort of, without knowing sigma at all, having no prior information about the covariance, produces an estimate that is close as scaled by this covariance matrix. And we do this using a mechanism that we'll call the Tuki Depth mechanism, which I'll explain, which is not really new to our work, although there's a modification of it that is critical, that really is specific to us. That was kind of one of our contributions. And maybe just something to notice is that this matches the sort of basically matches the kind of guarantee you can get when you know the covariance matrix exactly. So there's a theorem statement. I won't. I'll run out of time. But you basically get some covariance, some sample complexity that has these terms that we discussed earlier, plus some additional terms that I'll ignore for the purposes of this talk. Okay, so it turns out what we actually do, we give two different algorithms for this problem. One is this Tuki Depth mechanism I mentioned, another which we call the empirically rescaled Gaussian mechanism, and I'll explain both of those, at least at a high level. And we include both in the paper because they kind of give us different trade-offs among the things that they give us, like different extra properties from the algorithm. So the Tuki Depth mechanism, it gets this sort of essentially optimal sample complexity. The rescaled Gaussian mechanism has slightly worse sample complexity, but works for in addition to Gaussians for a larger family of distributions. And it just uses a fundamentally different approach, which is why we thought they were both interesting. I should mention that both, and this is really important, both of these algorithms, to the best of our knowledge, can only be run in exponential time. So one big open question that I'll come back to right at the end of the talk is getting these things to run in polynomial time, or ideally something that's practical and usable. Okay, so these should be just viewed as basic feasibility results for now. Okay, so since there's time for Q&A at the end of the talk, maybe I won't pause for questions, but if you want to put questions in the chat as we're going, maybe I'm happy to either try to digest them as we go, or that will at least give me a starting point for questions at the end of the talk. Okay, so the first approach that I'll talk about is this rescaling Gaussian mechanism. There's another question about slides, and I'll just answer it, that you have to look for the participant called Washington, and you pin that. Okay. Right, one approach is rescaling the Gaussian mechanism. So recall that if we knew the covariance matrix, the true covariance matrix of the data distribution ahead of time, we could just add Gaussian noise that was scaled to that covariance. And when we don't do that, what happens is that we end up with noise that is very large in certain dimensions, and in particular in the small directions of the Gaussian, resulting in possibly kind of ridiculous looking outputs. So our starting point is the idea, well, if we knew the covariance matrix, we could just add noise proportional to that. And the idea of the algorithm is just to try doing that anyway. So what we'll do is compute the covariance matrix of the data. So in the empirical covariance matrix. So that now has a dependency on X. And now we'll add noise proportional to that, scale to that covariance matrix. Okay, add noise to the empirical mean. All right, so Doing this straightforwardly is not differentially private. And the problem is that you could have two data sets that differ by one outlier. And that one outlier can completely drag off the estimate of the covariance matrix and result in a totally very different output distributions and a significant privacy breach. And this is not just, it's not even really a worst case problem. This could happen with very reasonable data. Just take any data set, throw in an outlier, and the presence of that outlier will be directly visible from the output. So the idea is to sort of somehow restrict our attention to a set of good data sets. And these are data sets that satisfy a natural concentration property, which actually shows up in Gaussian, data drawn from a Gaussian distribution. So roughly we'll say that a data set is good if relative to the empirical covariance matrix and the empirical mean, none of the data points are crazy outliers. Okay, so crazy outlier means many more, more multiples of the expected standard deviation than would normally appear in a randomly sampled Gaussian data set. Okay, so if we had data that our data satisfies this guarantee, then we could just add noise proportional to covariance matrix. And so the idea, and this is the part that takes exponential time, is to somehow project onto good data sets. So these are data sets that are that have no outliers in this particular way. So this is like a specific meaning of removing outliers that unfortunately takes exponential time to compute. But the idea is that if we've got a data set that is close to good, meaning removing a small number of data points would result in a good data set, then the algorithm will perform well. Then our algorithm will produce output and it'll be accurate. And if we start off with a data set that's very far from good, then the algorithm will just fail. It'll just throw up its hands and say, this data doesn't look Gaussian enough, I can't deal. And it's as I said, it's this projection step that ends up costing us. Okay, the other idea is to generalize, is to use this idea called Tuki depth. So the Tuki depth of a point in a cloud of data points is the minimum. It's the minimum number of points that I can separate from the rest of the cloud with a hyperplane that passes through my point in question. So the Tuki depth of the red point in this case is 2, because there's a way to split the data set with a hyperplane in a way that only 2 points are on like the wrong side of this hyperplane. Okay, so that's what the Tuki depth of a point is. So this is a standard notion from robust statistics. Higher depth means more central. And what's cool about the Tuki depth is that it always has sensitivity 1. That is, changing any one data set will change any one point will change the Tuki depth of a point in space by at most 1. And so we can do this thing called, we can run this thing called the exponential mechanism, which is an algorithm that sort of a standard generic construction of differentially private algorithms. So the trick here to doing this is that if we wanted, we can't sample from all of real space using this mechanism because the density wouldn't even integrate to 1. Like it's not a well-defined probability distribution. And never mind the fact that like it wouldn't be concentrated, it wouldn't have any of the properties we need. So the idea, this previous work by Liu, Kong, Kakade, and O also considered this Tuki depth. They use some prior information about the data matrix to narrow the focus of the Tuki mechanism to a subset of space. And our idea is that we can get rid of this need for prior information in this mechanism by sampling only from the subset of space that has sufficiently high Tuki depth. So we're just going to like ignore all points that have low Tuki depth and sample only from a subset of points with Tuki depth at least, let's say, n over 4. Again, so it turns out this algorithm is not differentially private, like as stated, but there's this additional, but it will be accurate. So that analysis is sort of uses some standard concentration mechanisms and machinery, and it's essentially all in this previous paper, this paper of Liu, Kong, Kakari, and O. But the idea is that we can somehow test whether or not this algorithm is safe to run on a data set, again, by defining a set of like good data sets. In this case, the good data sets are the ones for which this algorithm will behave similarly on X as it would on any neighbor of X. And so I guess I'll skip some of the details, but the idea is to just test if we're sufficiently close to if we're sort of sufficiently safe, sufficiently far from an unsafe data set. And if we're far from unsafe data sets, then we can just run the algorithm and it works. And if we are close to an unsafe data set, again, we just throw up our hands and say, hey, this data doesn't look Gaussian. I'm not doing it. Okay, so these are the two ideas. And they are both accurate, as I said, but they have different properties. And maybe one important thing is that neither of them is polynomial time in general. Okay, so our approaches work for things that are not Gaussian distributions, but they come with various caveats. So the Gaussian noise approach works on what are called Subgaussian distributions. So these are nicely concentrated distributions. The Tuki depth approach doesn't require really a concentration condition, but it does basically require some kind of symmetry from the distribution. So that points with high Tuki depth correspond to things that are close to the actual mean of the distribution, sort of the difference between a median and a mean. But I should mention there's sort of recent work by Liu, Kong, and O that generalizes the approaches in this paper for a much larger class of distributions, and I think that work will be available soon. So just a quick word on future directions. A big question for us is, can we get polynomial time algorithms for this problem? Exponential time in some sense seems like baked into the approaches we take. But the approaches we take are like, we have these two very different approaches, and for each one, it's sort of, there's a clear point that if we could come up with a polynomial time version of that, then the algorithms would work. Okay, and so in both cases, this has to do some kind of sort of a projection type operation, and that's something that we don't fully understand. Okay, there is a lot of interesting work going on, not on the problem I'm discussing in this talk, but on related problems problems on private estimation of Gaussian means and other distributions. So I think there's like a lot of ideas being generated right now, and lots of stuff to do there, and I think we'll see more advances in the next few years. Another big direction is to understand, never mind polynomial time, but can we get these algorithms to run, and like, can we get algorithms you'd actually want to run? And I suspect in particular these algorithms would really be useful in addition to being of interest on their own. I suspect they would be useful building blocks inside of algorithms like stochastic gradient descent or full gradient descent, when you need to get gradient estimates from a batch of users, for example. These methods would hopefully allow kind of tailoring to the gradient distribution automatically and get us much nicer practical performance from these methods. And finally, just sort of stepping back to the general problem of estimation and learning, we have, not just for Gaussians, but for lots of other problems, the general, the elements of a general theory here and there, pieces, but we're still very far from having a cohesive picture of what kinds of estimation problems can be solved differentially privately, especially for the especially for the case of this sort of general definition of privacy with 2 parameters, epsilon and delta, we don't really have a good like sense of which problems should be feasible and which ones shouldn't under this notion. For epsilon 0, we have a few more kind of generic results that give us a handle on what's feasible, what's not, sample complexity characterizations. For epsilon delta, it's a lot patchier, and that's partly because there's just a lot more space to explore, both in terms of techniques and in terms of, that means on the other side, proving lower bounds. Lower bounds becomes much harder. Okay, I'll stop there. I'm happy to take questions as they arise. So let's see. First question was on the best empirical results in this space for non-Gaussian data. I guess I don't really have a short answer for that. There's actually like a bunch of results on sort of practical algorithms for mean estimation that somehow adapt to the space the data comes from. Generally, they don't work as well in high dimensions. I think in low dimensional settings, we have a lot better understanding. But I sort of gave up on trying to make a bullet point about it on a slide because there's sort of lots of different approaches. I don't have a short answer to that question, unfortunately. Yeah, so Brendan asks about, do this sort of data-aware accuracy metrics correspond to like what is actually needed inside of an optimization procedure, like gradient descent or whatever you're using? The answer is I suspect yes, but I don't have like a theorem to back that up. Maybe someone else does. Probably there may well be other people who have better answers to that question, but intuitively there's sort of this is strictly better than just straightforward Gaussian noise. So at least in the world where O tildes are the things you care about, you're happy putting little tildes on your big O notation. The answer is yes, it's strictly better. Monica Ribeiro Diaz says, thanks for the talk. Yeah, so just to answer Monica's question quickly, because I know I'm out of time. Yeah, the idea is we're going to, the set from which we sample in this Tuki depth mechanism is sensitive. So we can't exactly describe the set. My slides are not, I think, updating for some, there we go. There's our, I apologize if somehow my slides were behind what I was saying the whole talk. I don't know. In any case, yeah, so the set from which we sample, like that is not public information. It's not released as part of the output of the algorithm. And what we argue actually is that sort of the boundaries of this set, they arise with such low probability that they don't matter in the privacy analysis. And that's how, that's how we, that's basically the kind of main ingredient in the analysis in some sense. And finally, Stephen asks well, okay, I'm going to skip the other questions because I think I'm out of time. So I'll hand it back to the organizers.
Feel free to spend another 2 minutes or so.
Okay, do we know, Stephen, I'm not totally sure I understand which Oracle. Oh, Oracle efficient in the same sense of if I had some kind of optimization tool. No, well, maybe, but the optimization problems would be really weird. That wouldn't be the standard one. So like, I don't have a good answer to your question, Stephen. It's an excellent question, and I don't know the answer. Do we know what the sample complexity is for the following approach? Estimate the 90th quantile sample using quantile, and then apply them as standard Gaussian monotone. Yeah, so Peter is asking, like, why can't we just kind of get a sense of like how, why can't we just get a rough sense of how big a ball we need to put around the data in order to capture most of the data, let's say, because that should be feasible to just get a radius, and then add noise scale to that. And the answer to the question is that only works. So that's a reasonable thing to do in many settings, but it will add tons of noise in the low variance dimensions if the problem is not well conditioned to begin with. So by well conditioned, I mean there's well-conditioned means the sort of variance in the large directions is on a similar order of magnitude to the variance in the small directions. So in fact, the whole point of getting stuck into this was to understand what happens in these like very, very poorly conditioned problems where the data is basically in some low dimensional subspace, but not quite, because there's still some variance in those directions. And then like how, can you automatically adapt to that so that you're not creating noise that kind of makes no sense for the distribution? And that's tricky. And in particular, like, I don't know how to do it without either exponential time or a lot more samples. So it is like a delicate problem. Any other questions? Okay, I'll stop there. Yeah, thanks.
Thank you for this wonderful, stimulating talk.